Hi, I want to take a look at how Newton's explanation of gravity and Newton's laws of motion explain Kepler's second law for the orbit of planets. Now, when Kepler wrote his second law, he observed that if you take a line from the sun to a planet and draw out the radius, and you then wait some period of time, draw the line from the sun out to where that planet would be, fill in the area of that portion of the ellipse, then the planets cover equal areas in this elliptical pie in equal amounts of time. So, to show that using Newtonian physics, let's think about the concept of angular momentum. So for a planet is freely moving through space. There's a force of gravity acting on it, while that planet, if it's traveling in any sort of direction, has an angular momentum with respect to the sun. So the angular momentum of that planet would be the cross product of the radius from the sun to the planet crossed with the linear momentum of the planet, the mass of the planet times the velocity of the planet. And the velocity of an object is just the derivative of the position. Well, the position, since it's in orbit, is the radius. So v is just dr dt. So what I want to do is explore this concept of r cross dr dt. So the first thing I want to do is let's turn this into a scalar. So if I look at the magnitude of the angular momentum, mass is a scalar, it's happy hanging out over here, I'd have the magnitude of this cross product, r cross dr dt. Well, these differentials down here, for all intents and purposes, are also scalars. So we could just multiply both sides by dt. And then I could divide both sides by m, so that tells me that the size of this cross product, r cross dr, is the size of my angular momentum times some small amount of time dt divided by the mass of my planet. Now, going back to the definition of the cross product. The cross product answers the mathematical question, what is the area of a parallelogram made by connecting vectors a and b end to end? So if there's r, and there's dr, if I turn that into a parallelogram, that's exactly twice the area that Kepler was talking about. So Kepler's area would be 1/2 times the magnitude of the cross product of the radius of a planet's orbit with the change in the radius of that planet. Well, that cross product is just the magnitude of the angular momentum divided by the mass times some small amount of time dt. The 1/2 is still there from the Keplerian area being half the cross product. And that says the area is, mass is a constant, 2 is a constant, and if there are no external forces, no external torques acting on that planet, so our system has to be the sun plus the planet, angular momentum has to be conserved. So that means this is a constant too. So area is directly related to time. For all segments of time dt, all planets need to sweep out equal amounts of Keplerian area. Thanks for watching.